All right, example number 9. We have a cylinder containing helium of 2 moles of gas at a temperature of 20 degrees Celsius. And we are also told, which we have to use up a periodic table, but we're told the molar mass of helium is 4 to the power negative 3 kilograms per mole. So let's write this down as given in our problem. So N for moles is 2. The temperature is 20 degrees Celsius. The molar mass is 4 to the power negative 3. Okay, so in part A, we are asked to find the total internal energy of the gas. That's U. Part B, we're asked to find the average kinetic energy per molecule. And part C is we would like to find how much energy would have to be added. I guess we'll call that E, I suppose, in order to double the RMS speed. So the VRMS new is going to be twice the old RMS speed. This is for part C. Okay, so first we are dealing with a helium gas, and helium is an ideal monatomic gas. And ideal monatomic gases, we can calculate the internal energy using the formula U equals 3/2 nRT. So we just have to plug in here 3/2 multiplied by 2 moles, multiplied by the gas constant, which is 8.314 joules per mole Kelvin. And you may notice I'm using Kelvin in here, so that means the temperature needs to be converted from Celsius to Kelvin. So remember, to convert from Celsius to Kelvin, you need to add 273.15 if you want to be more exact. So it's 20 plus 273.15, and this is all in Kelvin. So plugging that into our calculator, I got a value of 7,312 joules. That's the total amount of energy of all the molecules in the gas. Okay, now let's suppose we wanted to find the average kinetic energy per molecule. So here we use the equation 3/2 multiplied by Boltzmann constant multiplied by the temperature in Kelvin. So 3/2 times the Boltzmann constant, which is 1.38 to the power negative 23 joules per Kelvin, and then multiplied by the temperature in Kelvin. Remember that it's 20 plus 273, so it's really 293.15 Kelvin, and this gives you the average kinetic energy per molecule. And I get a value of 6.07 to the power negative 21 joules. That's per helium molecule. Okay, now moving on to part C. Let me scroll down to get a little bit more space. We are asked to find what the amount of internal energy or energy that needed to be added to the system. So such that the old or the new RMS speed, called V prime here, is twice the old RMS speed. So you may recall that the average kinetic energy again is given by 3/2 Boltzmann constant times temperature, but also kinetic energy is given by 1/2 the mass times the RMS speed squared. That's just the kinetic energy formula. So, I guess what we need to do is see what effect it would have on the kinetic energy, right? And I'm assuming that we're not adding more molecules, we're just adding more energy, right? Like thermal energy, just like U essentially. So in order to increase the internal energy, we want to increase the temperature. And so if you set 3/2 Boltzmann constant times temperature equal to 1/2 mVRMS speed squared, you can see that the temperature basically is proportional to the RMS speed squared. So if I, for example, double the RMS speed and it's being squared, that means that the temperature would have to be multiplied by 4 times. All right, so if the temperature increases by a factor of 4 without changing the moles, and U is equal to 3/2 nRT, and I'm going to change that temperature by a factor of 4, then I'm going to need to change the internal energy by a factor of 4, right? So essentially, my new energy is going to be 4 times my original energy. And my original energy I had gotten earlier was 7,312 joules. So if I multiply that out, I get my new internal energy is going to be 2.92, I guess, to the power of 4 joules. Okay? So that's not the answer you can see over in part C. So I need to find the change of that energy. So I'm running out of space, but essentially the change in the energy will be the new energy minus the original energy. So it would be 2.92 to the power of 4 joules minus how much energy it had initially, which is 7.312 to the power of 3 joules. So subtracting the old energy from the new energy, I would get an energy of 2.1935, or I'll just say 2.19 times 10 to the power of 4 joules. Okay, so first answer, that's the total internal energy, just given by 3/2 nRT. Then the average kinetic energy per molecule, using just 3/2 times the Boltzmann constant times temperature. And then if we were to double the RMS speed, we would actually essentially be quadrupling the temperature. And in order to quadruple the temperature, we would have to quadruple the internal energy. And so the new energy would be 4 times the original energy, right? So basically, the energy that we would have to add would be 3 times the original energy, which is just basically this answer here. Okay, hopefully that all makes sense. All right, thank you.